Okay, wonderful. All right, so these are the last two lectures of the quarter by me, and then there'll be a guest lecture by Natasha on Tuesday and paper readings next Thursday. And so we're almost there. Great. So logistically, I think last homework is out. I think it's due on the 31st. If you have some late days, feel free to use them. Project, we're going to do poster session during the usual class time, I believe, on the 4th. I think Zoe posted details. Refer to those details. But we're going to do it on the 4th, I think. And if you can't make it, just let us know and send us a video of yourself recorded explaining your project for 5 minutes.
Can you see like slides?
Yeah. Well, if you're not here, you mean?
Yeah, if we're not.
Yeah, just slides are fine. Yeah, slides are fine. Yeah. Cool. All right. Okay, so this is a video or this is a picture of inverse reinforcement learning in action, where this is from Google Maps. So Google Maps use a lot of human driver data to infer what people's preferences were and which roads they like to go down, which is more informative than just distances, right? And so they try to use picture data and so on to do like large scale inverse RL. And so you should check out Google's work on inverse RL. But that's topically relevant because today we are finally done with control as inference. And we're gonna do inverse reinforcement learning today. And then we'll either do offline RL or multitask RL on Thursday, depending on what lecture you guys want. Any preferences? Offline RL, multitask RL, both? Offline RL is just learning from prior data, and multitask RL is learning across tasks. Multitask, okay. Any other thoughts? Multitask, okay. We'll touch on offline RL a little bit, and then we'll do multitask. Cool. So, to kind of recap what we did so far, in control as inference, we had the graphical model. We said we're going to augment with optimality variables and give those optimality variables a likelihood proportional to the reward or equal to the exponential reward. And then we showed how this variational inference on this gives us policy gradient, right? So we just derived the evidence lower bound, show that it gives us policy gradient. We took the same evidence lower bound, we did dynamic programming on it, and we derived soft Q learning. Right, so gradient descent gives you policy gradient, dynamic programming gives you soft Q learning. And then finally, we showed how we can do this two-step process of learning a fake model and then doing posterior inference in this fake model. And this gives us something close to MPPI. Right? And yeah, that's kind of what we covered in the last lecture. Today, we're going to try and study inverse reinforcement learning or learning rewards from expert demonstrations. And we're going to go through hopefully 4 versions of this algorithm, right? From the most naive one to things that you use in practice. But let's start by thinking about why we care about inverse RL, right? So if we talk about this promise of reinforcement learning, we have this paradigm of an agent observes the environment, takes an action, the action is executed in the environment returns a new state and a reward, right? And then the goal is to learn a policy that maximizes the sum of rewards. That's been our premise so far, right? And the thing about, and we tried a bunch of different algorithms, right? We tried model-based RL, policy gradients, actor critic. And the thing about all of these algorithms is that they operate under the same assumption is that the reward is known and that it magically appears to you, right? It's like, the environment gives you a magical reward function. But in most problems, like imagine you have a robot that's operating the world, there's no reward function that appears out of thin air, right? And so in most problems, the reward function is unknown. It's often hard to specify. And it's like fundamental to the problem. How do you solve this problem if you don't know R? Right? And so inverse RL is fundamentally important because it tries to find a reward function that you can then use for forward RL. The problem with forward RL is it's undefined without a reward function, and reward functions are hard to specify. So we'll talk about why they're hard to specify in more detail, but the premise of inverse RL is that it's trying to find a reward function that you can then use for learning a policy. Okay, so reinforcement learning requires task specification. And what we mean by that is that the reward does not magically appear in most settings, right? It has to be manually specified. So for instance, in robotics problems, you might detect where the objects are. You might have a pose detector, or there's an example from one of Jan Peter's papers where they do pancake flipping. You can see they have like markers on the pancake and they tell me where exactly it is. And so once you know the state of the objects in the world, then you go and write a super complicated reward function, right? And so this is one that I took from the appendix of the PPO paper, right? The PPO for Dota 2 paper. And you can see that it has like approximately 20 terms weighted very carefully. And so reward design is not a trivial problem. Right? So when people want to solve problems with RL, they often, like as Andrew was alluding to in his lecture too, you either have a good optimistic exploration algorithm, which kind of works sometimes, but often what you do is you just like carefully specify the reward. So you figure out where things are in the world, and then you like have a bunch of different terms that weight these things that you care about, right? So for instance, in robotics, you often have like distance between the arm to the object and the orientation of the gripper with respect to the thing that you want, and then the height of the object above the table, and it's just like you're almost like hand specifying the problem. Right? And that becomes well, one, it's hard to do when you have perception, and two is that it just like requires a ton of domain knowledge, right? And so if I have to do this for every problem, it quickly becomes untenable. And so when you go to the practice of reinforcement learning, the algorithms are good and well, but often what makes it work is good reward shaping, right? So projects, if you find that things aren't working, just add more like fine-grained rewards. And like you can almost think of reward shaping as like dropping breadcrumbs along where you should go to solve the problem. So it's almost solving the problem for the agent, right? And so that's kind of, a problem. And we want to ask the question if we can do better than that. Yeah.
Reward shaping and other interpretations of exploration.
Yeah, I think exploration is smarter than reward shaping. Reward shaping is just like specifying a more detailed reward function. So exploration, I think, has uncertainty, and it's adaptive, it's convergent, right? Like the reward function?
Yeah.
No, you just like handwrite it. So like it's just like imagine that like there's this reward function that you get, right? You can have a reward function which is 0 or 1 if you succeed, or you can have a reward function that rewards you for getting close to this thing and this thing and this thing. So it's the same throughout training, but it's more carefully specified. So it's like cost function design in any like control problem, right? Although you guys do less cost function design here. There you're trying to just do tracking or something. Whereas in reinforcement learning, typically you don't know what trajectory you're trying to track. And so you have to like design the reward function to kind of guide you in the direction. Okay, so reward shaping is a thing lots of people do in practice, but we want to do better, right? So we want to be less constrained. We want to be able to get the benefits of reward shaping and so on without having to like manually specify. So how do we do that? The key idea in inverse RL is that you want to learn from demonstration, right? So just like we did in imitation learning, we're going to assume that there's an expert, and that expert comes in and says that we're going to give you a bunch of demonstrations of expert or noisily expert behavior. And then we're going to try and use these demonstrations of expert or noisily expert behavior to infer a reward function, right? And so imitation learning in what we covered in behavior learning was basically trying to do policy learning. So that you had expert behavior and you were trying to learn a policy with supervised learning or some variant of that. What we're going to try and do here is we're going to take these demonstrations and we're going to try and infer a reward function that explains these demonstrations. And then we're going to use that as a reward function for learning policies. Right? And so the paradigm of inverse RL is that we're going to like take these demonstrations, stick it into an inverse RL algorithm. Inverse RL algorithm will give you a reward function. You use the reward function for learning a policy. Right? Yeah.
Would behavior cloning be a way of it, like of doing?
So what behavior cloning would do, right, is it just kind of goes like from this, it goes from this thingy straight to like a policy, right? Whereas you can think of inverse RL as going from this thing to a reward function to RL, RL gives you a policy, right?
I mean, if you like half the reward function is binary as either like 1, you do that. You do the action that the like expert did.
Right. Yeah, no, there's variants of it that look like that. There's a few differences, right? One of them is that you have an explicit reward function. but you could do something like you just said, like a indicator. The other difference is that inverse RL is under the, like, you're going to get the policy under the you're going to do like in behavior cloning, you maximize likelihood under the distribution of expert data. So you do supervised learning. In inverse RL, you optimize reward under the distribution of the policy. And so it's like, if you remember how we saw that behavior cloning had the KL the wrong way. It's like inverse RL has KL the right way. We'll cover that in a second. Okay, but the premise of inverse RL, it's similar to imitation learning or behavior cloning, but it's that you're trying to extract a reward function, right? And so what you're trying to say is that you're trying to infer rewards from demonstration of optimal or noisily optimal behavior. And so the logic here is that noisily optimal behavior is kind of like optimum under some reward function. You're trying to find the reward function that explains this like noisily optimal behavior. So you're trying to invert the problem. Right, so let's go from expert data to the reward, and then the reward can be used for that's why it's inverse RL. So the assumption here is that we have to have some data that is noisily optimal. Right? So we already talked about behavior cloning, right? Like Alexa was just saying, we said we're going to maximize likelihood via behavior cloning. And the main differences between behavior cloning and inverse RL is that behavior cloning learns policies, right, with maximum likelihood or supervised learning. Inverse RL learns reward functions. And behavior cloning in itself assumes that you have no access. You don't need to assume access to the environment. You can just say, I get a bunch of data, I do behavior cloning, I have a policy ready to go. Inverse RL, because it's learning a reward function is not something you can run in the world. Okay? You need to go from a reward function to a policy to RL, and then you can run things in the world. So the premise of inverse RL is that you get a reward on a policy, and so you have to redo policy optimization to get something you can run in the world. And so if you're doing imitation through inverse RL, the procedure goes as you have demos, it goes to inverse RL gives you a reward. Reward goes through policy optimization. So any of the things we've done in this class gives you a policy. Now, the natural question to ask is, why do we do this? Why does this matter, right? And so there's a few reasons. But I think the key reason is really that imitation learning is all about generalization, right? So imitation learning doesn't make sense if you don't want to generalize. Because if you saw behavior and you're just trying to replay the behavior, you don't even need learning. You just like do nearest neighbor and you just replay the same thing, right? And so imitation learning is all like, if you were in exactly the same state as an expert saw, you already know what to do. And the only place where imitation learning makes sense at all is when you have generalization to new states, new objects, new positions, new environments. Right? And so the point of inverse RL is really to enable generalization over things like states, things like dynamics, and so on. Right? And so the point is, you're not going to change the task. Like the task has to be the same, because otherwise you can't. If you infer the reward for picking, it won't work for placing. Right? So you're in the same task, but you might have a different state. You might have different dynamics. And inverse RL, the premise of it is that because you're learning a reward function and not a policy, a reward function is independent of dynamics. And empirically, you find that like transferring a reward function generalizes better than transferring a policy. So you can almost think of it as a policy entangles reward, dynamics, and everything together. Whereas a reward function is disentangled from the dynamics. And so it like transfers better to new settings. Okay? And so the whole premise of inverse RL is really that you have to like deal with generalization. And so the question we ask is like, what if we learn something that generalizes better than policies? That thing is going to be a reward function. Yep. And so the idea behind inverse RL is really that if you have a reward function, it's independent of dynamics. And if it's independent of dynamics, then you're potentially able to have cross dynamics transfer. So you can change the like dynamics of your system. You can change the initial state of your system. Potentially a reward function transfers better. And so you can still get optimal behavior in new settings because you're not entangling the dynamics into this whole thing, right? And that's why you would even consider doing inverse RL rather than imitation learning with BC. Okay.
Like in comparison to behavior cloning, could this also allow the agent to like outperform the expert?
That's a great question. Like the imitation learning experts, or imitation learning methods we're going to talk about today, don't really let you outperform the expert because they're like assuming optimality. But there's an interesting class of methods that you ought to look at. It's called T-Rex, T-Rex, B-Rex, B-Rex. But they're really cool methods. They're from Scott Nico. And the idea there is that you can do an inverse RLS procedure to infer rewards. But it allows you to, like, they do it through ranking. So they say, like, let's rank trajectories. You say trajectory A is better than B, better than C, better than D. And they like have this ranking type objective. And the idea is if you can infer a direction of improvement, then you can extrapolate to be better than the demonstrators. And so that's the most compelling one I've seen of going better than demos, but in the typical inverse RL, will assume optimal.
Sure, but like in the Dota example,
Yeah.
like if they wanted to make like an agent that could outperform like the experts, they couldn't have just learned that.
I haven't seen it. Yeah. What they could do is they could get something that like for instance, if an expert picks something up suboptimally, it's not like inverse RL will magically let you pick it up optimally. But what it can do is let you generalize beyond maybe where the expert was successful. Okay. And the key point here is that policies and QR value functions entangle dynamics, where rewards do not entangle dynamics, at least in principle, right? And so what we're going to try and do with inverse RL is try to get something that transfers better to new settings. The other advantage of inverse RL is that unlike imitation learning, where you're taking the expectation under your data set, in inverse RL, you're like redoing policy optimization. You get a reward, and then you like train another policy with it, right? But you're doing it with the RL objective, not the supervised learning objective, which means that you have like less compounding error, right? So in imitation learning, you have the KL divergence between P star, your expert, and P theta. And in RL, you have the KL divergence between P theta and P star. And so the point is that the expectation is under the same thing that you're going to use at deployment, so you don't incur compounding error. And so I guess if you were to take away anything from here, inverse RL is useful for two reasons. The first being that you might be able to generalize better. And the second is that you don't incur compounding error as the same. And so I think in practice, lots of people still use behavior cloning, which is why I covered it in week 2. Because it's simple, right? But from a conceptual standpoint, like inverse RL has like a lot of nicer properties. It should work better. I think it's just like often to get it to work, there's going to be a lot of machinery, and that machinery is not worth it sometimes for just like bigger model, more data, simpler method, right? And so it's just a trade-off. I think inverse RL, if done right, will work better, but behavior cloning is really simple to use. Okay. So we want to learn rewards from human data. Imitation learning learns a policy. Inverse RL is going to get a reward function. That reward function will then be used for policy optimization, right? And so, yeah.
Sorry, because the expert demonstration will be for a particular task, and then so
it's the same task,
okay.
but potentially in new initial configuration or under new dynamics, right? Like let's say the friction of your arm changed and the reward is not going to change. I think that the argument for dynamics is easier to understand, as in like, okay, the dynamic might change, but your reward still, right? But the argument for initial states is a little more speculative, right? It's like if your reward is already provided, if your demo is already provided here, like why would that generalize to another initial state? And the argument there is usually that rewards are simpler than policies, and if rewards are simpler than policies, simpler things generalize. So that's usually the question. Great question, yeah. Okay, so we want to ask if this is a well-defined problem, right? And so we want to say that if I just got a bunch of data and I said, find the rewards, that's not like a well-defined problem in itself. And so we need to make more assumptions on the data, right? So we're going to make the assumption that experts are assumed to be noisily optimal, right? And so we'll get different inverse RL algorithms based on like what our definition of noise is, what our definition of suboptimality is, right? So one notion we're going to use is the same notion we used in controllers inference, like soft optimality, right? One notion that we use is like hard optimality, and we'll talk about whether that's well defined, but you have to assume that the expert is optimal in some sense, right? If it is just arbitrary data, then you don't know what explains the data, right? So like if I just got data and said, give me a reward, that doesn't make sense. I have to say that data is either optimal or noisily optimal according to some reward. And then I can try and infer that reward. And so that's the assumption we're going to make. We're going to make the assumption that experts are assumed to be noisily optimal. And we'll show how different types of optimality lead to different things. Okay. And to William's point from earlier, we're not going to do better than the demos in a way, right? We're going to do as well as the demos. There's inverse RL methods that like empirically sometimes do a bit better than the demos or denoise things, but in principle, there's no reason you should do better than the demos. Okay, so one way to conceptually think about this is inverse, like RL goes from rewards to optimal trajectories. Inverse RL goes from optimal trajectories to rewards, right? So the problem statement here is that in reinforcement learning, your state, action are known. Your transition dynamics is not known, but you can sample from it. Your reward is known, and you don't have expert policies or expert traces, right? You're just given S, A, transition dynamics, R. In inverse RL, your state is known, your action is known. You don't know your transition dynamics, but you can sample from the environment. So that's an important difference. You can sample from the environment in inverse RL. In behavior cloning, you cannot. The reward is unknown. The expert policy is unknown, but you have been provided expert traces. Okay? And so the difference in problem setting here is that you're gonna have known versus unknown reward. You're gonna have expert traces provided, and that's the main difference, right? So the point here is that we want to find R that explains the demonstration behavior. And then given a new dynamics, new state, anything like that, you do reinforcement learning to get a policy that you can deploy in new settings. Yeah. Okay. Some applications of this is, I think either the CMU or the Stanford car from the DARPA self-driving cars, and they have like traces of people trying to park. And then they try to infer what people's preferences are in parking, like which way is safe to go. And then they do inverse to infer a cost map, and they do use that cost map to do planning, right? Some other examples, again, from like early 2000s are trying to do like footstep planning. So they have this robot, I think Andrew Ng's lab had this. So they have this robot that's trying to navigate over different terrains, and they want to figure out like a cost map on where to place your footsteps, right? And that might be kind of, it's easy to provide a semantic cost map of where to go, but it's hard to provide one on where the footsteps should be. And so the premise of this kind of work was trying to infer cost maps in this setting. And perhaps the most, I don't have a slide on this, but perhaps the most well-known examples of cost learning or inverse RL are preference-based learning methods now, like for language models and so on. They're like, in essence, very similar to inverse RL. But all of them are trying to infer rewards from some sort of expert data. Preferences tell you like ordinal comparisons, and inverse RL gives you expert demonstration. That's a good question. I think they like joystick it, but then how do you control the legs? Yeah, I'm not sure. I'll look it up. That's a good question. Yeah. It's a paper from like 2008, so I didn't read it in too much detail. Okay. So why is this problem hard, right? So does everyone kind of buy the premise of inverse RL? So this problem is hard because it's underspecified, right? It's inherently underspecified. The same behavior can be optimal for many different reward functions. And so it's like an underspecified problem. You don't know reward and you don't know your optimal policy, right? You just have traces, and that becomes a hard optimization problem. You don't know the dynamics of your world. So it's like solving an RL, you don't know the policy. You have to, like we'll see that inverse RL needs to solve RL internally. And so it's like a doubly hard problem on top of RL, because you don't know the transition dynamics, you don't know the reward, you don't know the policy, you just have access to expert traces. That's it. Right? And then often you're trying to like measure optimality in a certain way. And like we talked about, like experts are optimal, and we don't exactly know what optimal means under what metric. And so defining these metrics to get good behavior can be difficult. But really the main difficulty of inverse RL is from problem one. It's that reward functions inherently underspecify behavior, right? Like the same expert behavior can be optimal for many different reward functions, but not all of them will generalize. And so you want to find something like, as Alexei was saying, you have a reward function that is one wherever you execute an optimal action at optimal state and zero everywhere else, but that's not a reward function that'll generalize. And so it's difficult to like find something that generalizes and do so in like the RL setting. Okay, so that's kind of the problem formulation of inverse RL. You're given expert traces, you assume them to be noisily optimal, you're given access to the environment, you want to find the reward function that best explains those noisily optimal traces, right? And in control, you often call this inverse optimal control. That's like the same problem, almost. But yeah, does that make sense? Everyone with me on the premise? Okay, so let's solve it, right? So the first thing we're going to do is we're going to try and construct a basic formula for inverse RL, and then we'll try to instantiate the formula. Basic formula is that you propose some reward function, a guess at a reward function R5. Then you're going to go and like learn an optimal policy or noisily optimal policy against R5. And this, remember, this is not a guess at a reward function. We're going to try and get an optimal policy. Then you're going to compare that optimal policy to some sort of expert data that you have, the noisily optimal expert data. We have to figure out what our comparison metric is going to be. And then we're going to go and propose a new reward function. And so the point is that we propose a reward function. You see what the optimal policy is. The optimal policy is going to be compared to the expert data. And that's going to give you a guess at how to change your reward function. Right? And so the point is that you want to do ascent or you want to do some improvement on your reward function based on how similar an optimal policy for that reward function is compared to the expert traces that you put. Right? And so you'll notice this is like an RL step. Right? So it's like this RL inside inverse RL, because if you propose a reward function, how do you know if the behavior like that results from that reward function is similar or not to the expert behavior? You have to do RL, right? And so essentially almost all inverse RL, there's like tricks now that make it better, but almost all inverse RL tries to do RL inside. Okay, so that's the basic recipe. We need to figure out how we're going to instantiate this. Does this recipe make sense? It's like take a guess, get a policy, see how good the policy is to the expert, take a better guess. Yeah. Okay, so that's the basic recipe. The assumptions we're going to make here are that reward is linear, right? Just for the sake of simplicity. For now, we'll make it nonlinear afterwards. And we're going to assume that we know the dynamics, right? When I say know the dynamics, like we're given a function of the dynamics, we can do planning or whatever. You don't have to just do sampling, right? So we're going to make some simple assumptions. And we'll know the dynamics. We're going to assume that the reward function is linear, right? Okay, now the assumption that we have is that our expert data is optimal, right? So what does it mean for expert data to be optimal? Like what information can we get from it? Like we know that we're given expert data and we don't know the reward function, right? But we know that the expert data is optimal. So what does optimal mean? That's right. So when you're saying it maximizes the sum of rewards, that means it's better than everything else, right? It's better than every other policy, right? So in some sense, a good reward function is one that evaluates optimal data, the thing that we've been given as our expert traces, and it's better than all other data, right? So if you're saying that like the expert traces that you got were the optimal for the reward function, that means the reward function would score that expert data higher than it scores all the other data, right? Otherwise, that data wouldn't be optimal for that reward. And so the basic premise of the first version of inverse RL we're going to do is that a good reward is something that evaluates the data you've been provided as higher reward than all the other data. Yeah. Simple logic. It's just saying you told me that the data is optimal. Optimal means better than everything else. And so what we're going to say is a good reward is something which treats optimal data as better than everything. That's it. Okay, so put it into like value function land. It says that the value function of pi star, or what you were given as the expert traces, is better than the value function of pi for all other pi. Right? So it's better than every other strategy. And so you're saying that like your reward function is such that v pi star r is greater than or equal to v pi r for all pi. And pi star is given to you, or like traces from pi star are given to you because those are your expert data. So let's see, let's try and think about what this means. This says that if I got, you know, data, I got some data picking up this law. It means that the value function, I'm going to choose the rewards as the value function of this thing is high. The value function of all other behaviors, right, or lower than this at least. Going back to our assumptions, if you remember our assumptions, we said we know the dynamics are known and the reward is linear, right? So going back to our assumption, we're going to try and stick in these assumptions into our condition. Our optimality condition says we want to find an R such that this constraint is held to be true. We want to find an R such that V pi star R is greater than V pi R for all pi. Yeah. Now, let's try and substitute this in. So if you look at the definition of a value function, it's just expected sum of discounted or expected sum of discounted rewards. And so the expectation under pi star of the discounted sum of rewards is greater than the expectation under pi of the discounted sum of rewards for all pi. Right? So it's better than all other false. Yes. And you're going to assume that rewards are linear. So if you know some features phi, your rewards are going to be like some W star transpose line. So the parameters of your reward are just the W stars. Yeah. So we're going to say we want to find the W star that best explains this state. Yes. Okay. So we've said V pi star R is greater than V pi for all pi. That's the definition of the value function. Yeah.
I didn't understand what's the phi is common area?
It's like some features of your state in action. So it's like you can choose any function approximator, like a neural net could be a function approximator. We're just going to choose a linear function. So we're going to assume that we know some features, like if you go back to old school machine learning, it's like new feature selection.
That's why the rewards are a linear function.
Yeah, that's right. Yeah. Sufficient statistics, as in there has to be an optimal policy that can be represented in phi. Okay, so given this definition of a value function, let's substitute in that definition of reward into this thing, right? So we can say that R is equal to W star transpose phi. And substitute that in here. You substitute that in here. And so what that tells you is that you can take W star out by linearity of expectation. And so what that tells you is that you can write W star transpose of this expected sum of features is greater than or equal to W star transpose of this expected sum of features under pi. So you're saying the expected sum of features under pi star, right? You say W star transpose the expected sum of features under pi star is better than W star transpose the expected sum of features under pi. Right? So let's recap what we did. We started with the reward is such that pi star is evaluated to be better than all other pi. We substituted the definition of the value function here. Then we substituted linear rewards here. And then we just took the, because it's linear, you can take the W star out, right? Linear and constant. And so now if we let's call these we call these things feature expectations often, right? So you can say that the condition that you get is W star transpose the feature expectations under pi star is better than W star transpose the feature expectations under all other pi. Yeah. So this is only true for linear rewards, right? But it's just saying that you want to find the parameter W star that tells you a reward function such that your feature expectations multiplied by W star is better for pi star than it is for all other pi. Okay, so does that make sense? All we did is we just took that condition at the top, we substituted linearity, we substituted linear rewards, and then we just use linearity. Now, what's a fundamental flaw with this equation? Just look at this equation. What's the problem with it? You're trying to find a W star such that this thing is true. Okay? That's the only condition you know. You only know the data is optimal. And equal.
How can we have an expectation of phi?
Its expectation of phi under pi star. So you know samples from the expert, right? So you know samples from the expert, and you know some features. So just take average sum of features under the expert, take average sum of features under your policy. Right? And you're trying to solve a constraint satisfaction problem. You're trying to say, let me find a W star such that this constraint is satisfied for all pi.
I guess then for policy, I mean, it works for all policies. So how do I know all policies?
Let's say you were able to sample all policies. Let's say there was a finite class of policies and you're able to sample all policies. It's a good question, right? So how do you know all policies? Good question. That's one issue, right? How do you know all policies? I think there's an even more pressing issue here. Yeah.
Are there like lots of trivial solutions?
Yeah, there's a trivial solution, right? It's just like you set W star to 0, and it's trivially satisfied. And so the problem with this is that it's inherently underspecified, right? If you're just saying that like something is better than everything else without any more constraints, it's just like an underspecified problem. And there's like infinitely many solutions, most of them which are useless. And so you need more constraints on the problem. And then there's the policy question. Okay, so any ideas on how do we make this less underspecified? Yeah. So you could force the norm of W star to be 1, and we do that. But there's this next idea we're going to talk about is this idea called max margin. And the idea behind max margin is that you're gonna force W star to be 1, let's say, right? But you're also going to say that you want to find a weight vector which is better than all the other, like you want to find a weight vector such that W transpose expected features for pi star are better than W transpose expected features for everything else with as big a margin as possible, right? And so how many of you have heard of support vector machines, SVMs, right? It's the same idea. Say in SVM, you're trying to find a classifier where you're trying to say the classifier has to have as robust a margin as possible, right? Here, what like you can think of like W as a classifier, the same way that you do in SVM. You're trying to say, let's try to find a W which has as big a margin as possible than when multiplied with mu pi star as compared to all other policies. And so the idea of max margin is that it tries to reduce ambiguity by finding the W which has as big a margin as possible from all other policies. And the reasoning is the same as SVM, right? So it's trying to say that like, let's try to find the weight vector, which gives you the biggest difference with all the other policies. And the hope is that is like not trivial, and that is going to generalize better. I'm unclear if that's true, but you have to make a choice on how you want to resolve ambiguity. It's an underspecified problem. One reasonable choice is that you will want to find the W that has the highest margin. Right? And so you like kind of formulate it like a support vector machine. The support vector machine, you're trying to find a classifier that classifies everything correctly, but has the highest margin from the data points. Here you're trying to find the classifier, which again classifies everything correctly, as in W transpose mu pi star is greater than W transpose mu pi for all policies, but has the biggest margin. Okay? And so the logic behind max margin is that you have inverse RL underspecified. You try to deal with ambiguity by trying to say, find the W that gives you the biggest margin. Does that make sense? Okay, so we're going to skip through, we have a bunch to get through. So I'm going to skip through the exact math. It's literally the same as an SVM, right? And what you're going to do is you can show that it's equal to like a problem that looks like this. Find the min norm W such that W transpose mu pi star is greater than equal to W transpose mu pi plus 1. Same way that an SVM does this, right? You just like divide by norm W and you do a little bit of manipulation. But the point here is that we're going to like deal with ambiguity by trying to solve a max margin problem, right? And that's what it's called, max margin inverse RL. It's pretty straightforward, directly applying SVM to the problem of inverse RL. Now the issues here is that it's like equally weighting all pi's the same, right? So it's saying that like this thing is greater than this thing for all pi's, and all pi's are treated to be the same, and so you're treating the margin the same across all the different policies, right? But some policies might be closer than others. And so what you can do is you can construct fancy max margin where you say that you're going to have like two changes. One change is that you're going to like, instead of having the margin be the same across all of the different policies, you can like choose a margin by hand, right? You can choose like a distance metric by hand. And then the second change you can make is that you can allow for some slack. So if you've seen robust SVM, the robust SVM allows for a little bit of slack, but you just try to minimize the slack, right? So the two changes to fancy max margin are you want to do max margin to minimize ambiguity. You're just going to allow the margin to depend on some hand-chosen distance metric, and then you're going to allow for some noise. Yeah, I was just thinking about, I don't actually know how they choose the margins by hand. Should look that up. But I think in practice, this tends to be more robust because it allows for some slack and it like doesn't weight everything the same. But the important thing to take away here is less of these details and more that more of this, like how do we instantiate this recipe, right? So we propose a reward function that is linear. We said we're going to know the dynamics, right? And then we said that we're going to compare this to expert traces, right? So we're going to say, we're going to compare this to expert traces by solving that optimization problem. And that optimization problem says that you're trying to find the W star, which is like better than, which ranks the expert feature traces better than everything else with as high a margin as possible.
Do we actually like do this optimization problem when we have like some?
Yeah, you do something like this, and you solve it with like CVX or something. Yeah, so like the reason we went from here to other things is that it becomes hard to solve this problem. But so the way we're going to do it to Noah's question just now is we're going to start with some random policy. We're going to have one element in our constraint set. Our constraint set is just going to be W transpose mu pi star. You can compute mu pi star because you know the dynamics, you know the features, and you have expert traces, right? And you're going to say it's greater than or equal to W transpose mu pi for the first pi for the first pi naught that you have. You're going to have a one element constraint set. So you're going to say my W has to rank expert better than pi naught. Right? This is going to give me some W. W will give me some policy. I'm going to take that policy. I'm going to add it to my constraint set. And I'm going to repeat, right? So you're going to like continuously grow your constraint set until you find something that is better than all policies.
Is this like straightforward?
Yeah, essentially. Yeah. Yeah, you can tell. Well, you would like define a programmatic handcrafting, like you would define a metric space.
But with the against the approach the size of time, all the
Like maybe one way of doing it is to like say measure the KL divergence between pi and pi star, and that's like your margin, right? And so it doesn't have to be handcrafted by literally by hand, but you just need a like programmatic metric.
Yeah, in the notation, there's two pi knots, but there's many different things, right? Pi knot is the pi star in the first iteration. The first pi knot is the pi star in the first iteration.
No. So pi star is always the expert traces.
Right, okay.
So pi star is always the expert traces. It's just that this constraint set is initially only over pi naught. I enforce this, I get a W. The W gives me a new pi. I add that to my constraint set. And then I find a new W. And then I repeat. Find a new pi 2, pi 3, pi 4. So my constraint, like the constraint that we had earlier, has to hold for all pi, right? So if you go back to this constraint, it's true for all pi. It's just, as Andy was saying, it's hard to enumerate all pi. And so what we're going to do is we're just going to incrementally build up the set of pi, right? So you're going to start with a pi, get an optimal policy, add it in, repeat. And so this gets better as you keep running it for longer because it covers the policy set more. But the optimization problem gets bigger and bigger because we're adding more and more constraints. And so typically when people are doing max margin IRL, they were doing it with linear policies, handcrafted features, and they were using like what do you call it, LP solvers, right? So like people are using like convex optimization packages to solve this. But the key point I want to make is that it like instantiates your recipe, propose a linear reward function with a W, tries to find tries to find a W which scores the expert feature expectations higher than everything else with as big a margin as possible, gives you a new policy, add it to your constraint set. So the point here is that you can run this and you will get some reward function W, right? And that W you can then use for policy optimization. So we want to see if this actually works, right? So this is the video from my PhD advisor, Peter Beal, where he flies a helicopter upside down. And this is back in like the mid-2000s. And so he was doing lots of acrobatics and things that were hard to specify rewards for. So he was trying to do stunts and flying upside down and things like that. Helicopter dynamics you can write down kind of. And so like here they're trying to do inverse RL with the version of this kind of.
Is that like a full-size helicopter?
No, it's a little. It's a little. Okay. So that is our first version of IRL, right? So we're just going to say we want to find something that scores the expert better than everything else. We want to do it such that you maximize margin and you solve it as an optimization. Right? Now, that brings us to our second method for doing things, right? To motivate that, let's think about why this might be difficult, right? Like some policies might have small margins, and like perhaps the most important thing is that we have to solve this with a convex optimization solver and with linear rewards. And we really want to get away from convex optimization solvers and linear rewards. Secondly, it's not always clear, like Andy was saying, how do you specify this margin? How do you know which things are close and which things are not? And it's often not clear how to optimize this with a stochastic optimization tool like gradient descent, right? And so what we're going to try and do next is try to derive an algorithm that is much more amenable to large models, to gradient descent, and like it's just easier to use. It tends to work better. And the key idea is we're going to go from this like hard notion of margin. We're going to like our hard notion of margin said the expert is better than everything else, right? And we're going to try and go to a softer notion of margin, which is going to say the expert is more likely than everything else. And that's going to make everything easier. So turns out we've talked about soft optimality before for like 3 lectures, right? And so what we're going to do is we're going to reuse that framework. We're going to reuse this controllers inference framework. Just as a reminder, controllers inference, we talked about variational inference, and we talked about how it gives us maximum entropy RL. We're going to try and derive maximum entropy inverse RL using the same framework, right? And so the point that we made when we're doing controllers inference is that human behavior is not optimal. Human behavior is noisily optimal, right? And so this is like the perfect use case because we're saying we got real human data, and real human data may not have been optimal. It may not have been maximizing margin from everything else. Real human behavior is probably soft optimal, right? It's just saying that the good behavior is more likely than the bad behavior, but doesn't mean you only do the good behavior. So the point of maximum entropy inverse RL is that rather than saying that you are better than everything else, you're saying you're like softly better than everything else. And so we're going to go from this hard notion of a margin, which is just like saying A greater than B, to a softer notion of margin through this controllers inference type framework. Yeah. So the intuitive idea of maximum entropy IRL is it's just trying to impose, like we said in our recipe, we need to like compare. We need to compare to expert traces. In max margin, we had a hard notion of comparison. We said it's better than everything else. In max and IRL, we're gonna have a soft notion of comparison. Right? That's it. Okay, so let's kind of try and derive it from first principles, right? And yeah, again, we might get into the controllers inference math, but y'all are experts now, so it'll be easy. So okay, let's remember the controllers inference graph model, right? So you have optimality variables. Optimality variables have likelihood equal to the exponential rewards. And if you look at the like joint distribution of trajectories given that you're optimal, it's equal to the distribution of a trajectory from the prior times the exponential sum of rewards, right? So it's saying that things that have higher rewards are more likely, things that have lower rewards are less likely. And so you can just derive this by taking all the probability distributions here and multiplying them together. Okay. So that's control as inference. And so we say that P tau is our prior behavior, which is uninformed, right? It's not trying to be optimal. And then we're trying to go from that to our posterior, which is P of tau given optimality, which is saying that what is the behavior that is likely, condition that you're being optimal, right? And we said that that is proportional to the exponential sum of rewards. So what we were trying to do in soft RL or like maximum entropy RL was we said we knew R and we we're trying to do the posterior inference problem. In inverse RL, we're going to say we don't know R. We know that we're sampling things from the optimal posterior, and we're going to try and find the R that best explains the data from the posterior. Okay? And so what we're going to do in maximum entropy inverse RL is saying that we're given S and A from optimal data. So we observe that it's optimal. We know that the data is from the posterior, right? So we know that it's from something that is noisily optimal. Like, can we find the reward function that best explains this data, right? And so one way of thinking about, does everyone know how like map works, maximum a posteriori optimization, right? Like basically if you have a posterior, you're trying to find the parameters that best explain the posterior, right? And so what we're going to say here is that that should actually be map, not map selecting. But the point here is that we're trying to say that we are being given samples from this distribution. We're given optimal or noisily optimal trajectories. That's what the expert gives us, right? The expert gives us samples from P of tau given optimality. And we are trying to find the R phi that best explains, right? And so we're trying to find the R phi that best explains the samples from the posterior P of tau given optimality. Yeah. And so let's try and write this out a little more formally. Yeah.
I'm a little confused because in the controls and framework, those optimality variables are hard. It's like one or nothing.
Yes.
Right. So how can you get like soft information like that?
So the optimality is hard, but the likelihoods are soft, right? So it's like the likelihood of a trajectory is a probability, right? And so like none of the trajectories necessarily go to zero, right? So it's like the optimal, even when you set optimality to 1, the likelihood of the trajectories don't go to 0. They just get weighted according to the exponential itself. And so saying that the depending on the reward scale, things that are more likely are weighted high, but they're never 0 likelihood. So the softness is in the probabilities, not in the optimality pair. Good question. Okay, so what we're going to try and do is solve this problem. So assuming that the reward is parameterized by some parameters phi, we're going to try and find the parameters phi that maximize the likelihood of the trajectories that were sampled from the expert or the noisy expert, conditioned on the fact that we were optimal. So it's saying that like this is giving you the likelihood of the trajectory being produced under some reward function phi, conditioned on the fact that you were optimal, right? You're trying to say, try to find the reward function that best explains this, that maximize the likelihood. And so you're trying to say, this again, it's math, not max likelihood, but the point here is that you want to find the parameters of your reward function. So if you can think of this thing as parameterized by R phi implicitly, right? And you're trying to find the parameters of the reward function that maximize the likelihood of the data that you actually saw from your expert. And the point is that because it's not hard optimal, like nothing should have likelihood 0, right? Everything will have some likelihood. Or yeah. So what we've done here is we've said that optimality went from reward to a posterior. Now we've given samples from a posterior, and we want to find the reward that best explains it. Right? And so our inverse RL problem is going to be finding the parameters phi that maximize the likelihood of the data that we actually saw. Right? We're going to go with
This is just like normal supervised learning.
Yeah. Ish. We'll show how it's a little bit more complicated than that, but it's like similar problems in maximum. Normally in supervised learning, right? What you would do is you would parameterize this by some theta, right? Normally you like learn a neural net or something that goes from X to Y, right? And then you kind of learn the parameters of the neural net directly. Here it's like like a little more complicated of a parameterization. So it's going to look a little different than supervised learning. Basically, the point is that I'm not directly learning something that takes an optimality and gives me trajectory. I'm instead trying to learn a reward function, right? And the reward function is connected to this thing through this like I'm trying to learn the parameters phi, and this thing is connected to the reward function parameters through this like very specific relationship. Right? So it's not just like black box learning the parameters of the supervised learning model. It's like connected through that specific relationship, and that's going to result in a slightly different. It'll become more clear once I work out the exact form. But the important thing to remember here is that maximum entropy RL said we are trying to find this thing. Given R, we want to find this thing. Inverse RL says given this thing, we want to find R. Right? So it's inverse. Okay. Questions? The point is we're still doing control of distance. We're just going to find R rather than the posterior. We're saying we're given samples from the posterior. Find the R that best explains. So maximize the likelihood. Yes. So let's try to write it out and see what this looks like. And it's going to have like a really intuitive meaning once we work through it, right? But let's try and write out what the likelihood of like what this posterior looks like in terms of phi, and then we'll work out what the learning algorithm becomes, right? So as we saw earlier, the likelihood of a trajectory given optimality is 1, it's proportional to, the coordinate is proportional to the likelihood of a trajectory is exponential in sum of rewards. Right? And the reason it's proportional to is because this thing is equal to P of tau comma optimality divided by P of optimality, right? It's like by Bayes rule, there's a denominator, and we usually ignore the denominator, but it's going to be important here. So we said that P of tau given optimality is proportional to P of tau times the exponential sum of rewards, right? And so this thing is the thing that is parameterized by phi, right? So if I want to take like log prob of this thing, right? Like I want to like find the like max of this thing with respect to phi, right? This thing, the right-hand side does depend on phi through this exponentiated sum of rewards. Okay? Now, the important thing here is that if I take the log of both sides, right, you get log of P of tau plus log of exponentiated sum of rewards, right? This thing doesn't depend on phi. It's the prior, so we can ignore it first, right? So what we're going to do then is we're going to say that we can ignore the P of tau because it doesn't depend on the reward, just the prior. And then we can say that this thing is equal to the exponentiated sum of rewards divided by the integral of the exponentiated sum of rewards, right? So the important point is that proportionality, which we ignored till now, is going to matter now, because if you notice, both the denominator and the numerator depend on phi, right? So it's R sub phi, right? Like reward shows up in both the numerator and the denominator. So you can't just, if you're trying to find the max of that thing with respect to R or R phi, you can't just like throw away the denominator. Right? And so we're going to have to factor in the denominator, but the point here is that the posterior is proportional to the likelihood of the trajectory times exponentiated sum of rewards. And the like this denominator, which we're going to call the partition function z, right? That's often called the partition function z, is going to be just the integral of the numerator, right? Just the integral of the numerator, but it's hard to estimate because again we hit integrals in the denominator. Integrals in the denominator are bad. But we're going to call this our partition function z. We're going to show how we're going to like deal with it. Right? But the important part here is that we want to solve this optimization problem. We want to maximize the log likelihood of the trajectory given optimality with respect to phi. And that means it's the log of this thing. And both the numerator and denominator have phi, right? And so the important thing to remember is that it's going to be like some x r phi by some z, which also depends on phi. And you're going to take the log of this and you're going to maximize it with respect to phi, right? And so the important thing we're going to have to figure out is how do we deal with this integral in the denominator, which is a pain in the ass, right? And so that's what the next couple of slides are going to be about. But the main point, zooming out, is that we got some data. We said it was noisily optimal. We want to find the reward that best explains it. You get the posterior, And then you want to do map to find the parameters of the reward that best explain samples from the system. Yeah. So this is going to be inverse RL, but it's soft because we didn't assume any of the, nowhere did we assume optimality, we only assume soft optimality. Yes. Okay, so let's keep going. It's going to be difficult to compute analytically, this objective, again, because if you write down this objective, right, you're going to have like log of the numerator, which is going to be simple. So log of x sum r is going to be simple. It's just going to be sum r, right? Numerator is good. The denominator, you're going to have like a log of an integral of something, something, something. And that is like a pain to compute, right? When you have a log integral, that. And so the partition function, the log denominator is going to be hard to compute, but the gradient is going to be nice and easy to compute. And so we're going to work out with the gradient. And when I'm trying to maximize this objective, I'm going to do it with gradient descent anyways. And so we're going to show that the gradient looks good. And if the gradient is good, then everything is good, right? And so, okay, so any questions before we get into the details? Okay, let's keep going. So this is our posterior. It's like the likelihood of a trajectory given optimality is exponential sum of rewards by integral exponential sum of rewards, right? And we want to maximize it with respect to phi. And so if you like, if you substitute log of this thing into here, you get log of exponential sum of rewards minus log z. Let's call this thing z, right? You get minus log z. Now, this thing is easy to compute. The first term, log and x cancel out, right? And so you just get, the first term is the expectation of trajectory sample from the expert of the sum of rewards, right? The second term is this like log z term, which is like kind of a pain to compute, right? And so what we're going to try and do is take the gradient of this and show that gradient log z is much better to deal with. Yeah. So literally what I did is I took this definition, stuck it in here, and then log and x cancel. That's it. Great. Okay, so the first term is easy to compute. The second term is hard to compute. But let's take the gradient and see, like, just pray for the best, you know? And so we're going to take the gradient. And the first term, we see that this thing doesn't depend on phi. It's just expert data, right? And so you can stick phi into the, like, the only thing that depends on phi is the rewards, right? And so you can stick phi inside, and then the first term becomes just the expected sum of gradients. And so it's saying that samples takes an actions from the expert and take the expected sum of gradients. Right? So it's easy to compute. You know how to compute that expectation because you have samples from the expert. Right? You just take samples from the expert and compute. And you know the reward function, you chose the reward functions. And so you can get the gradient, you can get the samples. The first term is easy to compute, right? Even with the gradient. Now the second term, you have this like grad phi log z term, right? And that's the one that's going to be a pain. So we're going to use a few different identities. The first is this chain rule, right? So saying the gradient of log z with respect to phi is 1 over z times the gradient of z with respect to phi. Right? And then we're going to define z as the expected, like it's the integral of the numerator. So it's like the integral of likelihood of a trajectory times exponential sum of rewards in a trajectory, integrate over all trajectories. Right? That's the denominator. The numerator was exponential sum of rewards of a trajectory. The denominator is integral of that over all trajectories. Yes. So we're going to use these two identities and stick it in to get a form for grad phi log z. Okay. And so just substituting, grad phi log z is going to be 1 over z times grad phi z. So we're going to have 1 over z times grad phi z. Let's work out the second term a little slowly. Right, so this 1 over z is going to be this 1 over z. And now we need to find out what grad phi z is. So if you have grad phi of the integral d tau exp r phi tau d tau, right? Now help me work it out. What happens next? Bring it in, right? And so this thing doesn't depend on phi, so bring it in. And the gradient of exp is exp, right? And so you're going to have d of tau exp r phi tau But you're gonna have chain rule again, so you're gonna have a grad phi r phi tau theta. Right? That's it. You just brought it in. You apply chain. Okay. So this is like all we did is we applied these two identities, right? And we got our second term is 1 over z phi tau x r phi tau grad phi r phi tau d. Now, if I look at this thingy, and if I look at these thingies, like, does this remind us of something?
The reinforce.
Yeah, it's kind of like reinforce, but there's a little more to it, right? So, if I like, let's go back. If you go back to this thing, right? You see this posterior, right? It says PF, let's rewrite this in a form that's more immediately obvious. It says PF tau given optimality is equal to PF tau times x bar tau divided by integral PF tau x bar tau, right? Which is 1 over z PF tau x bar tau, right? And so that's literally the term we had back there, right? So what that means is that if I go back to my expression here, this thingy, right, is equal to P of tau given optimality, right? So it's equal to your posterior, but it's under your current reward function phi, right? And so let's transform this and it'll become intuitive in a second, right? But the important part is that, oh, I have it. The posterior is proportional to P of tau times x bar tau divided by z, which is the integral of P of tau x bar tau, right? And so the second term, we can now simplify to another expectation, but it's an expectation under the posterior. So saying the first term is the expectation under the expert data. And then the second term is an expectation under the posterior under your current reward function phi. So it's saying that like this is basically what max and RL computes. Right? Max and RL tries to compute the posterior. It tries to say like we show that RL is equal, max and RL is equal to posterior. So it's a max and RL is literally trying to compute this. It says things that are higher reward are higher, things that are lower reward are low. That's it. And so we're saying the first term is expectation of gradient under expert data. And the second term is saying expectation of gradient under the optimal policy for the current reward function. Right. So what does this mean intuitively? Right. It says push up the gradients along the experts. And it says push down the gradients for the soft optimal policy under the current. Right. And so if I was to take a gradient of the reward function, it would push up stuff for the optimal data. It would push down everything for the optimal policy computed under the current reward function. So the thing to note here is that the only way to actually get this posterior is by doing RL. Right? So you do max and RL on your current reward function. That gives you this policy, gives you this soft optimal data, and you say push up everything in the expert data, push down everything from your optimal policy or your soft optimal policy. Right? And so intuitively, let's try to connect it back to our like IRL, the first version of IRL we did in max margin. We said we're going to be better than everything else. Here we're saying like we're going to make our stuff more likely and everything else equally more unlikely, right? And everything else here is going to be like on policy data. So we're going to say under a current estimated reward function, we find the optimal policy and we'll like push it down. And the next time we'll find a different reward function, different optimal policy, and we'll push it down, right? And so the way that this algorithm is going to work is it's gonna have an update on phi. So phi is going to get updated using the objective above. Then you're going to try and find an optimal policy to solve the second part of the equation, and then get a new update on phi, update phi, resolve optimal, and repeat, right? And so the point is you have an initial get to the reward. It allows you to compute this gradient because this term is easy to compute. We'll do RL with the current reward function, get data, push that down, push optimal data out. Then we get a new reward function. You resolve RL, push that down again, and then you keep getting this gradient and you repeat. Right? So it's still doing RL in the inner loop, but it's like all soft. And it's like you can just do this gradient descent, no constraint optimization, no nothing. You solve this objective with gradient ascent. You alternate between updating the reward parameters and solving RL for that. You estimate the gradient. Like you have to do RL to estimate it. But the nice part here is we saw that the log likelihood was hard to estimate. The gradient is easy to estimate, and the gradient just goes between RL and update on rewards. RL on update. So that's just max and RL. So let's see if we go back to our recipe. It doesn't have to be a linear reward, but it could be. And all we're going to do is we're going to change our comparison metric to pushing up expert data, pushing down on policy data. And so it's easier than max margin IRL to use with a big neural net or anything complicated. And yeah, so the pseudocode here is something like this. You start with a random policy, weight vector if you don't have a linear function. You find the soft optimal policy under that reward function, right? So you just do RL, max and RL. Then you take a gradient step on the reward function, get a new reward function, resolve soft optimal RL, get a new gradient for W, update W, resolve soft optimal RL, and repeat. And when you're done, you're going to find both your optimal W and your optimal policy at the same time. Because inside every step, you're also solving for your optimal policy. You're going to solve both for your optimal W and for your optimal policy, right? Or optimal like reward function and your optimal policy. The nice part is that if I want to go to a new domain, I can take even if the policy doesn't work, I can take the reward function and apply it to the user. Okay? And that's nice. Okay, just to make sure we fit in time, these are some examples from some friends at Oxford who apply this to like a little car that they drove around and try to like navigate on grass versus different terrain, etc. And it works in practice. And this is like the most commonly used IRL algorithm. Okay? But we're going to have to make some changes to it to get it to work in practice, right? The first thing we're going to do is we're going to try and relax these two assumptions. The first assumption being that the reward was linear, and the second assumption being that the dynamics were known, right? And the nice part about this objective, right, is nothing in this objective needs the rewards to be linear. Right? If you go back to the thing that we computed, right, where we computed, the thing that we computed, like just gradients. This could be on neural net. They don't have to be on weights and linear things, right? Like you can just represent this whole thing by neural nets. And so the nice part about maxent IRL is that you can go all the way to like nonlinear functions like a neural net, and you can just use auto differentiation to compute these gradients, right? Like nothing in the framework says that you can't do that. The thing that is more problematic is that inside every RL step, you have to run inside every RL step, you have to run RL to convergence. And that's like kind of a pain, right? And so we want to like avoid running RL till convergence every time, right? And so the reason you have to run until convergence is because this thing is basically the optimal policy, right? And that's kind of okay. And so now the logic we're going to use is we're going to do something lazy. We're just going to improve the policy a little bit, right? Which means that we're going to have a policy, we're going to improve it a little bit, and we're going to ask if we can still compute this gradient, even if we didn't compute some stuff to optimality. Okay? And so the way we're going to do that is that we're going to use, okay, so the problem here is that it's going to be biased, right? So if I take this gradient, this thing is coming from the expert data. Yeah. And this thing is coming from the optimal policy under your current reward. Right? The problem is if I don't have the optimal policy, I cannot compute the expectation of the second. And so let's say I like did some lazy optimization where I stuck in some like P suboptimal instead. The problem is the expectation is wrong. Right? Like it's just under the wrong distribution. And so how do we fix it? If you didn't see my next slide. So what we want to do is we want to not have to go to optimality every time. We're going to use a different suboptimal policy. How can we still compute this gradient even if I didn't have the optimal policy? Oh, off policy RL? Yeah, you can do off policy RL, but even in off policy RL, you have to still compute the like you still have to run the thing till convergence, no? But I think you can compute this expectation in an easier way, right? If you think back to, did we cover this? Um, yeah. Yeah, that's right, that's right. I think we covered it in policy gradient at some point. But you basically use this idea called importance sampling, right? And importance sampling says that, let's say I didn't have samples from P. I only had samples from Q. Can I still compute expectation under P? I can if I like reweight those samples by P over Q. Yeah. So you're gonna get expectation under Q by taking samples, or expectation under P by taking samples from Q and reweighting them by P over Q. The logic is simple, right? It's just like if you have expectation, it's going to be Q times P over Q, whatever, and then you're going to get expectation. The Q and P over Q will cancel. Okay, so what we're going to do is we're just going to apply importance sampling to this problem, and we're going to say, let's sample from some wrong distribution Q, but we're just going to weight by P omega, which is like the optimal policy, divided by Q. Right now, so all we did is we took this objective. This is optimal policy, or PW is optimal policy. We're just going to sample under some suboptimal policy Q. We're going to do importance sampling. Okay. Now, this is still hard to compute, right? Because like, how do I get this ratio? Yeah. Yeah, it's a good part. How do you get the ratio, right? But the nice thing about maxent RL is that you know that this thing is proportional to the prior times X R. You know the optimal policy is proportional to your prior C times XR, right? That's what soft optimality means. And so if you do some like little bit of gymnastics, you can show that like the importance weight is going to become like exponential sum of rewards in the numerator, and the product of like phi theta is going to be Q. So it's going to be the product of likelihoods under your current policy in the denominator and exponential sum of rewards in the numerator. And so the point here is that it's going to be like this thingy is going to be proportional to X sum of rewards. This thingy is going to be just like a product of the policy likelihoods at every time step, right? And so you can just divide these things to get the importance weights. And so the nice thing is like everything is computable then, right? In the sense that you can use a wrong policy and you can still compute the expectations. If there's no free lunch though, in that like these weights will become really high variance. Like as you're multiplying a lot of little things together, you're like gonna have really high variance weights. But the nice part is that I don't have to go to convergence every time. I can just like improve my Q to be a bit better, a bit better, a bit better. And I can just correct it with this importance weight. Yeah. Yes, but the numerical difficulties will get in taking the will happen in taking the log, perhaps. Then. Is that true? Yeah, I guess you could do that. That's a good suggestion. Yeah.
You do like a hot initialization to like reuse the weights.
Yeah. Yeah, that's what we do. That's what we usually do. Like you'll run a continuous optimization where you're just like you retain Q from the past iteration and you just like warm initialize it every time. But you just like change the importance weights because you're biased. Yeah.
What was recency bias? You're just like multiplying what P that is proportional to.
Yeah, there's like a denominator term, right? There's like you're saying PW tau is proportional. It's equal to basically 1 over Z P of tau times X bar, right?
So do we have to incorporate that Z here, or is that?
Yeah, that's a good question. And the denominator, I guess, is P over tau times pi, right? And these guys cancel, but there's going to be a Z missing. So I think you're right that it's going to be a little if you don't split the C. That's a good point.
Where is the P of tau?
Oh, so like you could think of So the denominator is going to be like the likelihood of a trajectory. So it's going to be likelihood of the initial state times the likelihood of the initial action times the like dynamics. Right. And so you can take the likelihood of all the dynamics as like P of tau basically. And then the likelihood of the policy separate. But William makes a good point that there's like a missing C, which I kind of missed in my computation. Let me look into it, William. I'll get back to you. But you're right that there's a missing Z, which means that it's a constant, but it's going to be scaled differently for different time steps of this whole optimization. So and it's gonna like change the scale of this thing compared to this thing, right? And that's the tricky bit. I think in practice what they do is they just like multiply by some constant. But that doesn't sound right. Let me get back to it. I'll post an answer. Yeah, it's a good question. Okay, so the way we're going to do this now is that rather than solving till optimality every time, you're only going to improve a little, and then you're going to correct with importance swings. You're still going to max that IRL, but you're not going to like go to optimality every time. You're just going to do policy optimization on your reward function a little bit, and then correct for your reward gradient with this importance swing. And so that makes it lazy. And so now you have a procedure where you're improving your reward a bit, improving your policy a bit, improving your reward a bit, improving your policy a bit. And rather than reward a bit, policy for convergence, reward a bit, policy for convergence, you do both a little bit at a time. And this is some work from my former lab mate Chelsea, and she was basically trying to do like dish tracking, right? So she had like people provide some examples of doing dish tracking, and she was able to extrapolate the new initial configurations and so on using this like lazy optimization strategy. And the thing that she found the most difficult when she was doing this was like getting these weights to not flow. Okay, so we have 5 minutes left. I'm going to really quickly get to like the thing that we really care about, which is the thing you do in practice, which is that you often treat this like a GAN, right? So when you think of inverse RL, you treat it like a GAN. You can think of your policy as your generator and your reward function as your discriminator. And so what you're trying to do is you're trying to find a policy which generates trajectories that the reward function cannot discriminate between the optimal and the like generated trajectories, right? And so there's this nice paper on like the connection between GANs and energy-based models and inverse RL. But essentially, what it boils down to, don't worry about the math here, basically you can show that this thing under this choice of discriminator is equal to the GAN equation. And intuitively, this makes sense because you can think of the reward function as discriminating between optimal policies and suboptimal policies, and the policy kind of generate behavior under your current reward, right? And so what people will often do on practice is that they use this algorithm called Gale. And what Gale does is it just trains a GAN where it trains a classifier between expert data and non-expert data, and use the log likelihood of the classifier as rewards for the policy, right? So it's trying to say, like, for the policy, you're trying to get things that confuse the classifier. And for the reward function, you're trying to classify between optimal and suboptimal behavior. And so if, Apurva and William, you're doing bikes, right? It's like a similar method where you're trying to say, you're trying to classify between optimal and suboptimal behavior and using some like slight massaging of the log likelihood as a reward function. And that comes from this connection. Like you can derive a GAN directly from this by choosing this choice of discriminator. But the intuition is more important. It's like the generator is trying to confuse the reward. Generator is the policy is trying to confuse the reward function is trying to separate optimal from suboptimal.
In general, though, GANs is like really stable convergence.
Yeah, which is why IRL is hard to use. Yeah. Good question. Which is why often behavior cloning is easier to use because GANs are hard to use. IRL is just as hard as it can. Any other questions? Okay. Some examples of this in action. So those are some in simulation, but I thought these were cool. They're like teaching an agent how to walk using this technique called adversarial motion priors, which is essentially an IRL technique, where they teach it style. And so, yeah, I think for the first time, we actually got through all all the steps. But yeah, that's inverse RL. And yeah, see you guys Thursday. You need this, Michelle?
Yeah.
Scanning off.